Good morning. Good morning, everyone, and welcome. Welcome to AP Chemistry. We're going to review Actually, I'm not going to review anything. We're going to go over the 2018 free response questions. Yes, Isaac. Cooper was upset about that this morning. I don't know why. Maybe they're doing like an early life Jonas Brothers film. Hi, Maggie. Of the rise to fame. I mean, you could do like a rise to fame movie. Just watch Camp Rock. Yeah, basically the same story. Hi, Zach and Micah and Isaac. Good morning, everybody. I didn't get a chance to, Maggie. I missed it. Well, my wife and I will probably watch it tonight after the kids go to bed. Cooper hates on everything, Micah. No, on the Jonas Brothers. Jello, Naya. I prefer Jello with the G. Yes, but my wife went to Fizz this morning, so just enjoying my fancy Fizz drink. Just some Dr. Pepper. So autonomous in Utah, they have these like soda bar places that just mix random drinks together. So this had Dr. Pepper, like coconut, vanilla, raspberry puree, cream. Yeah, it's just, I don't know why, but there's like all these Utah places. There's all these soda places that just add like a bunch of random stuff to Coke. Yeah, no, Louisiana. I wouldn't see it being popular in Louisiana. They're from Louisiana. He was there's another high school teacher that is streaming his lessons on Twitch, and he rated me this morning, so autonomous kind of stuck around. Yeah, the Shaw chemist. I should give him a shout out. I should set up a bot to do like shout outs and stuff. I need to get on setting up a bot to do stuff. I think I'll do that this weekend. Yeah, I know. I got to get Nightbot and all that other stuff. Oh, Austin said it was weird. Maggie said it was good. Yeah. I got a lot of stuff I got to do to up the quality of my Twitch stream. Yeah. Gotta love Chris Pratt. Looking forward to what? Maybe I'll do something. I need to mess with my work. I have some of my valence electrons rewards. I need a green screen, up the production quality, get a green screen around the back up. I made a mock-up banner. Nice. I have to see it. I will warn you, my high school team is really good. Like, we have diamonds and plats. So just a heads up on that. Isaac, you might have to reload the stream. DJ doesn't even play League. That's weird, Isaac. I wonder why. I'm on my end. I'm not dropping any frames. Everything's looking good on my network settings. So. Here I'll link my team, Autonomous. Give me a second. This is the Brighton team. That's our starting roster. Quarantine's going good, Naya. I'm glad it's Friday. I'm excited for the weekend because even though for a lot of people weekends are the same, for me it'll be nice to take a break, not have to worry about getting stuff ready to go in the morning. It's my wife's birthday this weekend, so I think we're gonna order some sushi, do something. Yeah, no, quarantine's good. We watched The Social Network last night. Had never seen it. It's pretty good. Isaac, is that a good idea to get your braces off the morning of the AP test? Yeah, it's a pretty good movie, DJ. I was kind of it was cool to see. All right, let's get started so we don't run out of time. What questions do we want to go through from the 2018 exam? 2018 exam. Oh, sorry, Shockham. If you're trying to send a link, I've got links disabled. They should. So, Naya, dentist office and things like that should be open for business starting tomorrow. PK is just the negative log of the KA, Joel. He's not really bronze 1. He just hasn't played very much. He's more of like silver level. He just hasn't really played that much this season. Okay, so let's see. I've got a request for 2D, 3, 1E, 2. Isaac asked about that one in Discord the other day, Anna. But we can still go through it for sure. 3E. I've got all of 3. Maybe we'll just do all of 3. 2E. Maybe we'll do 2 from like D on. All right, let's start with number 1 and see kind of where we get. Okay, those are scoring guidelines. Okay, let's zoom in. Yeah, probably Isaac. 6 will go quick. Okay, so let's look. Number 1. Noting 1 is our sodium hypochlorite ion. Determine the oxidation number. Okay, so 1A is dumb because the sodium hypochlorite ion, the oxygen. Here, let me show you. So because oxygen is slightly more electronegative, oxygen gets its normal charge. Let me double check. Yeah, this is, remember I was complaining about the hypochlorite ion when I talked about assigning oxidation numbers. So between oxygen and chlorine, oxygen is more electronegative, so it gets its normal charge of -2. Sodium has an oxidation number of +1, and the chlorine is going to have an oxidation number of +1. Yeah, so fluorine is the most electronegative, then oxygen, then chlorine in terms of electronegativity values. So oxygen is almost always going to be -2 unless it's by itself or it's paired with fluorine. Then it might be something otherwise. Or in like hydrogen peroxide, it's a -1. Weird one, but yeah. So oxygen's -2, chlorine's +1, and so then our oxidation of chlorine is +1. So that's 1A. B is just a factor label. C, using the balance equation for oxidation reduction reaction, terminal reaction is limiting. Again, we just say, oh, right, because there's a coefficient of a 4, the sodium hypochlorite is limiting because they're all the same concentrations and volume. So this is our limiting reactant. We get our graph. According to the graph, what's the temperature change? This is such an easy point, right? You just take final minus initial. 32.0, 33.0, so this is what, 32.5, and this is 20. So 32.5 minus 20 gives you 12.5 as your delta T. Right? Then part E, the mass of the reaction mixture inside the calorimeter is 15.21 grams. So we use our answer from D to get the mass in part C. Then it wants us to calculate the heat. So on part E, we're going to use a Q equals MC delta T idea, which I'll put this back up here in a second. And so we just plug in and solve. So they tell us the mixture is 3.94 joules, which is kind of cool. It's not 4.18, it's 3.94, which is a little interesting. Yeah, I know. I'm switching over. I'm just grabbing all the units. So we found the delta T in part D, which is 12.5 degrees C. We find the mass from the problem. They tell us it's 15.21, the mass of the mix. They give us C, and so we just calculate Q. So we use 15.21 grams. They tell us the C is 3.94 joules per gram degree C. Delta T, 12.5 degrees C. So we just multiply those together. 15.21 times 3.94 times 12.5. We get 749 joules. And 3 sig figs would be proper here. So 749 joules is our Q. Right, so that is E1. Okay, then E2 is the one that a couple people had some questions on. So E2 then asks, using the balanced equation for the oxidation reduction reaction and your answer in part C, calculate the value of the enthalpy change in kilojoules per mole, include the appropriate algebraic sign. Okay, so there's a few things we got to remember here. Number one, in terms of that algebraic sign thing, we have to remember that the Q of the reaction equals the negative Q of the calorimeter. And so if this is the heat absorbed by the calorimeter, then the Q for the reaction is going to be negative because the reaction is releasing heat. And so we have to remember that sign of negative. This is an exothermic reaction. It's releasing heat. That's why it got hotter. Now, in terms of calculating in kilojoules per mole, right, we want to know how many kilojoules are in 1 mole, right? The problem, we were using, 0.5 molar solutions. So we know that for every 0.5 moles of solution, there's 1,000 milliliters. And we know that 5 milliliters of my solution released negative 749 joules. Right? And so it should be a big number. 1,000 divided by 0.5 divided by 5 times 749 gives me basically 300,000. Oh, that's joules. Shoot, my bad. 1,000 joules is a kilojoule. So we get negative 300, and that's 3 sig figs. It's 299.6, so negative 300 kilojoules per mole. Now, we do have to be careful here because this is not quite right. And the reason why it's not quite right is because I didn't specify per mole of what. We identified the limiting reactant was the sodium hypochlorite. So this is for every 1 mole of sodium hypochlorite, right? But in the reaction, we used 4 moles of sodium hypochlorite. And so technically this number should be multiplied by 4. I should have done that. I should have actually done that first. There should be a first step here, sorry guys, where it should say how many kilojoules per mole of reaction. And for every 1 mole of reaction, there are 4 moles of the sodium hypochlorite. That should go in there. And then the rest is right. And so it actually should be negative 1,200 kilojoules per mole. Is that what the answer key says? Let's look. Let's see if I'm off. I might be. I'm afraid I am. Sodium hypochlorite's limiting. 12.5 is the delta T. 749 for the joules. Oh no, there it is. Negative 1,200 kilojoules per mole. So yeah. Okay, cool. So they did it, instead of doing it as a factor label, they did it to where they just found the moles of sodium hypochlorite, and then they did a 4-to-1 ratio to get us the moles of the reaction, and then we did divided by. So how did I get it multiplied by 4? Let me recap my math on that, Lauren. So we have to be careful of a few things. So in this example, right, we're mixing 5 milliliters of each of these. And they're all the same concentration, okay? So we want to focus on which one's limiting. If we look at the stoichiometry, it's a 1 to 4 to 1 ratio, so that means this one's limiting. So that means the sodium sulfate and the sodium hydroxide are not going to completely react, and so we can ignore them and we can just focus on the sodium hypochlorite because it's the one that's going to get totally used in the reaction. And so we want to know, remember that delta H is always kilojoules per mole of reaction as written. And for the reaction as written, there are 4 moles of sodium hypochlorite. So that's why in my conversion, this is why I should have done this 4 in here first, because the way I should set up the problem is how many kilojoules are there for every 1 mole of reaction. And for every 1 mole of reaction, there are 4 moles of the sodium hypochlorite. And this is important because this is what was, this is important because this is what was limiting. And so you would always want to use whatever's limiting here. And then from here, you use the concentration, how many moles are in a liter. Then we used 5 milliliters of the solution, and we got this many joules from our previous problem. And then 1,000 joules, not 100, 1,000 joules is 1 kilojoule. So this is how you end up getting negative 1,200. So yeah. So it's just because of the coefficient. That's why we multiplied by 4, Lauren, is because it has a coefficient of 4. Okay. Is that it for this problem? There's F and G, but I think you guys, no one had any questions about F and G. So let's go to number 2. What questions do we have on number 2? 2E, 2D, 2E. So let's look at 2. Oops. So on problem 2, we had to draw a mixture here, right? So we just had to draw a picture. that represented an equimolar mixture. So they wanted you to draw the reactant diagram that would yield the products. So if we have 1, 2, 3, 4, 5, 6, 7, 8 nitrogens, then we need 8 NOs and something. NO and NO2. So we need 8 NOs and we would need 4 NOs and 4 NO2s or something. Whatever. You have to just count and make sure that numbers match up. And you had to shade in the nitrogens. Part B, assume mechanism equimolar, calculate the value of the equilibrium constant. Oh, they gave you delta G. Oh, shoot, you shouldn't have been able to do B. Did I tell you to skip B and C? I think I told you to skip B and C. Because we didn't talk about how to do those calculations. So let's go to D. The skeletal structure of the HNO2, so it should just be single bond, double bond. That's what gives you the best formal charges. Not a double bond on this oxygen, but a double bond on this oxygen. Hybridization, the nitrogen, because you should have a lone pair here, it should be sp2, right? So this should be sp2. Then we have a titration to produce, so it's an acid, nitrous acid, student bubbles into O3 into distilled water. Assume the reaction goes to completion. HNO2 is the only species produced. Determine the concentration of HNO2 in the resulting solution is 100 milliliters. Okay, so we have a weak acid with a strong base. Use a titration curve to determine the initial concentration of the HNO2 solution. So we know, let's see, do we know the volume? Oh, 100 milliliter sample. Okay, so we do know the volume. So we just use the equivalence point. So let me jot down some info to do this problem. So whenever you're trying to find concentration and you have a titration curve, you should always do equivalence point. We did, Naya. I can go over it again real fast. So I'll go over both of those. I'll talk about why the one structure is better than the other here in a second. So I'll talk about that, and then I'll also talk about this titration calculation. So 100 milliliters of our HNO2, 20 milliliters of 0.100 molar KOH. All right, so we can see that the equivalence point is obviously at 20. It's really nice. They give us a nice, even, perfect equivalence point. So let's go over formal charges of the HONO, the nitrous acid, and then we'll go over the titration calculation. So two possible Lewis structures based on the valence electrons are these two. So you may have arrived at either one of these structures. So you could have gotten either one of these. Both of these follow the octet rule. Both of these use the correct number of valence electrons. Okay, but the formal charges are where these structures start to fall apart. So in this structure, we would say that this hydrogen has half of this bond, so it's got 1 electron. Hydrogen starts with 1 electron, it has 1 electron. This would give it a formal charge of 0. This oxygen, 1, 2, 3, 4, 5, 6, has 6, ended up with 6, formal charge of 0. This nitrogen, 1, 2, 3, 4, 5, has 5, started with 5, formal charge of 0. This oxygen, 1, 2, 3, 4, 5, 6, has 6, started with 6, formal charge of 0. So in this structure, everything has a formal charge of 0. That means it's a really, really good structure, right? Best structures have formal charges that are 0. However, in this structure, this oxygen gives us a problem because it only has 1, 2, 3, 4, 5, right? Half the bonds and the lone pairs. So this would have a formal charge of +1. It's missing a valence electron. And this oxygen over here, 1, 2, 3, 4, 5, 6, 7, and so this guy is -1, right? So our formal charges of 0, 0, 0, 0, 0 are much better with 0, +1, 0, and -1. Is there cases where multiple structures have formal charges of 0 but aren't resonance? If all of the formal charges are zeros, and the bonds are all like the atoms are in the same order, and there's multiple with all zeros, it should be resonance at that point. Yeah, I can't think of a case where it wouldn't be resonance, TJ. So, for example, if in this structure this one had been like +1 and this one had been -1, then I would argue that these two are resonance structures. But because this one is all zeros, this is the objectively better structure. All right, now we use 100 milliliters of the HNO2 solution, right? It's a 1-to-1 ratio, 1 hydrogen, 1 hydroxide, and so we can just use our little cheater equation. Whenever you have a titration, if it's a 1-to-1, just use this equation. So the molarity of the acid, you don't even have to convert to liters. What is it, like 0.02 or something? Yeah. Well, a 2-to-2 is a 1-to-1, Isaac. But yeah, if you had if you're doing like a redox equation and they both had the same coefficients, it's fine as long as their coefficients are the same. Technically, if you want to take into account the coefficients, you can divide by the moles, and that makes this equation always work. Yeah, if you do that, this equation will always work, with this moles being the coefficient. If I want to do proper sig figs, we can estimate down. We can estimate this as 20.0, so it should be 0.02000. Yay, cheater equation. It just shortcuts stoichiometry. What, Naya? Wait, what? Are you asking about this mole thing? So this is the coefficients. If you just plug in the coefficients here, this equation will always work. For like a titration, if you ever want to look at the equivalence point. Yeah, so if you ever want to try to determine, if it's not a 1-to-1 ratio, you have to plug in like 1 and 2 or 2 and 5 or whatever it might be. But it's because in 1-to-1, those are just ones, we ignore them. But if you plug that little corrective factor in there, it'll always work. All right, so that's E. Determine the initial concentration, check. Estimate the value of the pKa. Oh, so remember for a titration, right, pH equals pKa at the perfect buffer. So 3.3. 3.3. 3.3. Might try reloading, Naya. It shouldn't be. I don't have any lag time on my end, so might be a lot of people on Twitch. Who knows? So yeah, the pKa should be 3.3. Because remember, for an acid-base titration, pH equals pKa at the perfect buffer. And that's the perfect buffer. Halfway to the equivalence point. Is that what the answer says? Let's see. 2, you had to draw. We skipped B and C. D, we have our structure. Lines can be used. sp2 was our hybridization. 0.020 molar. We're done with school when we're done with the test, Micah. You literally don't have to watch anything when you're done with the test. pK is about 3.4, 3.3, 3.4. Yeah. So they don't even give an explanation. They just say as long as you approximated it, you're good. That's really interesting. You didn't even have to explain yourself. You just had to write a number. No, school's over. Oh my god. They have made it so we're not allowed to assign anything after the 15th of May. Letter F. During the titration after a volume of 15 milliliters added, which species? So this is more of like a buffer. So on that one, I would say you're probably plus or minus 1, Logan. So if you said anywhere like 3.3, 3.4, or 3.5. Yeah, so some of you have AP test the next week, Naya. But if you don't have an AP test on the next week, then you're done. Okay. So Logan, I think I answered your question about room for error. You're probably plus or minus 1 on that last digit. I don't know how lenient they were when they were actually grading it. But yeah. Probably that's kind of a few too many sig figs. They didn't grade for sig figs on that problem, but I would be wary of putting that many sig figs on there, because this is 2, 3, 4, so you'd have to say like 3.2 or 3.3. I don't know, we could zoom in on it. I mean, because that's 3, and that's 3.5. Yeah, 3.4 is a better estimate. Okay. Letter F is a buffer problem. I'm going to skip the buffer problem because there's not going to be buffers on the AP test. So, yeah. Let's look at number 3. Answer the following questions relating to iron and its ions. Iron 2+ and iron 3+. Back in the day, this used to be called ferric iron and ferrous iron. Because technically, Isaac, you know how to do it, but I don't want to go over the explanation. So remember, buffers have been removed from the AP test. Now, acid-base problem. So this part E, at least part A, is a valid question for the AP exam this year, but letter F, they've kind of taken off this idea. But I mean, you could, it's past halfway to the equivalence point, and so you know you're going to have more of the conjugate base. Yeah. No, wait, I thought, oh no, maybe you're right. Yeah, you are, Isaac. I got him backwards. I haven't used the terminology in a long time. So we have iron 2 and iron 3, ferrous and ferric iron. Write the ground state configuration for the Fe2. Man, electron configurations. Woo, throwback. So if we pull up a periodic table, right? Iron's in the middle of the periodic table. And so we could do they want you to do a complete? I wonder can you get away with doing noble gas notation? Oh, you can. They allowed noble gas notation. So we're going to do that. So if we're going to do iron, we're going to start with argon. So we would do, so Fe, which one did they ask for? 2+. Right, it would be argon, 4s2, 3d5. Now I'm going to be careful on this, right? 1, 2, 3, 4. Oh no, it's 6. Sorry. Okay, so iron is argon 4s2 3d6, right? We count 6 in. So don't forget, remember, we're on the 4th row, but we're filling in the 3d. It's been a while since we've done that. So 1s, 2s, 3s, 4s, right? So 4s and then 3d. The d's are one behind. So this is for normal iron. So remember, when we make it a 2+, we have to remove the electrons, and the electrons get removed from the 4s orbital first. So you can write it as 4s0, or you can just write argon 3d6, which I think might be the preferred way for the AP test, but they should give you credit either way. So argon 3d6, that's our iron 2+. The radii are given. Let's Let's see. So we have the radius. Iron 2 plus is 92. Iron 3 plus is 79. Use the principle of atomic structure to explain why the radius of the iron 2 plus is larger than the radius of the 3 plus. Well, as we remove electrons, right? If you have your... So here's your iron atom. We talked about when you remove electrons, the number of protons remains constant. And so there's a balance between electron-electron repulsions and the attraction to the nucleus. And so if you start plucking off electrons, there are fewer electrons, but yet the same number of protons. So that same number of protons pulls on the electrons more tightly. And so we would say... no, Isaac. We would say that as we remove electrons, as we form cations, our radius shrinks. Okay? And that has to do with there being less electron-electron repulsion. That's kind of the term you would go with, is there is less electron-electron repulsion, which I believe they say here. Both ions have the same nuclear charge, however, the greater number of electrons that outer shell of the Fe2 plus, greater electron-electron repulsion, leading to larger radius, right? So there we go, greater electron-electron repulsion. So the iron 3 plus has less electron-electron repulsion, that's why it's smaller. Iron 3 plus ions interact more strongly with water molecules in aqueous solution than iron 3 plus ions do. Give one reason for the stronger attraction justified using Coulomb's law. It's a greater charge. A greater charge means more attraction. That's Coulomb's law. Coulomb's law is that the force between two charged objects is equal to the magnitude of their charge and the distance between them. So you actually could say either one. You could say that because the 3 plus is smaller, there's less distance between the water and the iron 3 plus, or you could say because it has a greater charge, there's more attraction. So you could have said either one, and the scoring guide should say both. Yeah, the smaller size allows to get closer, check, or iron 2 plus is greater than 3 plus. Yeah, you don't have to say Coulomb's law, but just remember charge and distance. Directly proportional to charge, inversely proportional to distance. They love Coulomb's law. So that's an easy point there. All right, part D. A student obtains a solution that contains an unknown amount of Fe2 plus to determine the concentration. We do a reaction, okay? So we're going to do some sort of oxidation reduction reaction. You could, there's a constant that is here. This is a proportionality. There's a constant that you need. I can't remember what the constant is, but yeah, you could calculate the force if you knew the constant. But it's an assumption because you're just focusing on one factor. You have to calculate all the other factors to really get the actual force value. Because Coulomb's law assumes that they're in a vacuum, if I remember correctly. Okay, write the balanced equation for the half reaction. This is actually really, really simple. I hope you guys didn't get thrown off on this. Yeah, it does, Isaac. I think. I don't know. I haven't done very many calculations with Coulomb's law. So we want to write the iron 2 plus goes to iron 3 plus. Plus an electron. That's it. That's all you had to do. Ta-da! So this is part D. Right? Iron 2 plus, there's nothing else there that needs to be balanced. You just have to make sure the charges are balanced. 3 plus plus an electron makes 2 plus. They told you it was oxidation, so you know it's losing an electron. And so that's why it's Fe2 plus goes to Fe3 plus plus an electron. Done. Easy. Point. Check. Oxidation half reaction. I don't think so. They shouldn't count that wrong. I mean, if you want to be technical, I doubt they would count you wrong for that, but they do specify in the question Fe2 plus aqueous to Fe3 plus aqueous. I highly doubt they would take off for that, but I would write it just to be safe. But yeah, I really doubt they would take off for that because that's not what they're trying to test here. Okay, the student titrates a 10 milliliter sample, calculate the value of iron 3 plus if it takes... Oh, so this we can use my modified cheater equation for, right? Plugging in the coefficients. Or you could do stoichiometry, or you could do factor label. Either one should get you the right answer here. So let's see, 10 milliliters of Fe2 plus. We're trying to find the molarity. And then we're using 17.48 milliliters of potassium permanganate, 0.0350 molar. The coefficient of the iron is 5. The coefficient of the permanganate is 1. So if we look here, let me show you the work I got set up. Okay. So 10 milliliters times the question mark molar divided by 5, because that was our coefficient. Because it's a titration, Isaac, you just have to plug in the coefficients. So 17.48 times 0.035 times 5 divided by 10, I get a concentration of Fe2 plus. Do we have 4 sig figs or 3? 3. And we get 0.306 molar, which is correct. And so then if we go to the answer key, they say that you have to, they say 1 point is earned for calculating the number of moles, but then they say it may be implicit. So you don't have to actually say how many moles there are. You just really have to get this correct calculation. If you get this correct concentration, you automatically get those 2 points. Done. So yeah, you can do it as either a long factor label, or you could do it as just using the equation with the coefficients. Part F, I hope you guys got, or I guess part F says, explain why the 25 milliliter volumetric flask would be a poor choice for delivering the required volume of the Fe2 plus solution. So we're supposed to do 10 mils. Do you guys remember what a volumetric flask is and is used for? I haven't done a great job of explaining those things. So remember, a volumetric flask is this guy, and it has a single line on it. So a volumetric flask, I had some really big ones in my classroom. Whenever I would make a stock solution, I would use those to make a good amount. The thing is, volumetric flasks are really good at measuring a specific volume, 25 milliliters. But they don't have any gradations on them. They don't have any markings. They can't measure anything other than what they are, right? So this volumetric flask measures 25 milliliters. That's it. So if you needed 25 milliliters of something, this would be great. But if you needed anything other than 25 milliliters, this wouldn't be a good way to prepare it. So volumetric flasks are good for one volume and one volume only. They're very precise for that one volume, but that's all they're good for. And so that's why in the question, right, a 25 milliliter volumetric flask would be poor because we only wanted 10 milliliter sample, right? A burette would probably be the best choice, right? Because a burette, you can deliver a specific volume that you need. Graduated cylinder would be okay. Beaker would be pretty garbage, and volumetric flask doesn't, you'd have to guess even worse. You'd get less than 1 sig fig. So burette is the best for determining a volume because you get 4 to 5 sig figs. Graduated cylinder is good because you get 3 to 4 sig figs. No, because remember with a burette, right, you'd fill it up to 25, and then you could open it until it drops exactly 10, and then shut it off. So that would give you the exact 10. So you could deliver exactly 10 with a burette. Graduated cylinder, right, you could use a 25 empty, because these are the empty volumes, right? So you could use an empty graduated cylinder, and you could fill it up till the 10 mark, and then that would be good to go. Okay. So, yeah. In terms of getting a good number of sig figs, burettes are the best, then graduated cylinders, beakers are not good. And a volumetric flask, if you wanted 25 milliliters, volumetric flask would be fantastic. But if you don't want exactly 25 milliliters, it's not going to be any good. Okay. In a separate experiment, the student is given a sample of powdered iron that contains an impurity. The student uses a procedure to oxidize the iron to Fe2O3. The student collects the following during the experiment. So we had this with the impurity, and then we had this. Calculate the number. So this is just a mole conversion, right? So you just use, you take the 7.531. Yeah, my papers are stuck. Yes, a volumetric flask would be greater than a graduated cylinder if you wanted 25 milliliters rice. A volumetric flask would potentially be better than a burette if you wanted exactly 25 milliliters. So if you had a 10 milliliter volumetric flask, that would be good too. All right. 7.531 grams of Fe2O3. So we would need the molar mass. The molar mass of iron 3 oxide is 160 grams per mole. Technically 159.7 grams of Fe2O3. So you can do this a couple different ways. You could say 1 mole of Fe2O3. You could say 1 mole of Fe2O3 has 2 moles of Fe. 1 mole of Fe is 55. This is part G. 3G. So we need, what is iron? It's 55 point something. 55.8. Alternatively, you could just say in every 159s of Fe2O3, there's 111 grams of iron. That would work too. So what I'm doing is this conversion, I'm figuring out how much iron is in that much iron oxide. 7.531 divided by 9.7 times 2 times 55.5. You get 5.27. Actually, let's do 4 sig figs. 5.267. So this is the pure iron. And then the iron impurity was 6.724. So G, calculate the number of moles, check. H, calculate the percent by mass. So you just do 5.267 divided by 6.724 times 100. That would give you the percent purity. .34%. And then lastly, letter I asks if the oxidation of iron in the original sample was incomplete, so that some of the 7.3 gram probably was FeO instead of Fe2O3, would the calculated mass percent of Fe in the original sample be higher or lower than... Oh, I hate these problems. So these problems are hard because you have to kind of think through them. So really, you got to be careful on how you think through these problems, right? So first off, how does FeO compare to Fe2O3? Well, FeO is a 1-to-1 ratio, where Fe2O3 is a 1-to-1.5 ratio. So FeO has more iron as a percentage than Fe2O3 does. And so that means that of the 7.531, more of it would be iron if some of it was FeO. And so if more of it was iron, then my calculated mass percent would be higher than otherwise. Let's double check that logic, see if that works. So we get... oh, we were supposed to calculate moles. I went straight to grams. Oops. -1 for me. So 5.267 grams, we get the 78.33%. The calculated mass of Fe would be lower than the actual mass percent. The calculated mass where, though? Oh, yeah, the calculated mass would be lower because the true mass would be higher. And again, that's why it's confusing, because you have to specify, okay, is this the hypothetical situation or the real situation or whatever. So let's see how they word it. They say a sample that contains any FeO will have a higher actual mass percent of Fe than a completely oxidized sample would have. Therefore, when the moles of Fe are calculated, assuming the mass of the sample is Fe2 or 3, the calculated number of moles and hence the calculated mass will be lower. Boom. Okay. We've got a few more minutes. Someone asked for one of the other ones. 4a, says Haley. So 4... in the tables above gives the molecular structure. This seems like, yep, intermolecular forces. Really important topic. This is going to be a big idea. Make sure you understand question 4. In terms of the types, relative strength of all the intermolecular forces in common, explain the boiling point of CS2 is higher than COS. So in other words, why is CS2 stronger, right? If it has a higher boiling point, that means it's stronger. Why is carbon disulfide stronger, have a higher boiling point than COS? Now this is a little tricky because technically the CS2 is a non-polar molecule, so it only has dispersion forces. And this is where it gets a little tricky. That's why I'm saying this problem is tricky. Is because if these two molecules had the same molar mass, then you would bet that COS would be stronger because it's polar. However, because sulfur weighs twice as much as oxygen does, it turns out that the dispersion forces in CS2 are stronger than both the dispersion and dipole-dipole forces in COS. This is a mean problem. But it's a problem with a purpose. They want you to recognize that the boiling point is higher, therefore the intermolecular forces must be stronger. And so even though this only has dispersion forces, the dispersion forces in CS2 must be greater than the dispersion and dipole-dipole forces in COS. Let's see what it says. CS2 has only London dispersion forces, while COS has London dispersion and dipole-dipole. The London dispersion forces in CS2 are stronger than the combination of London dispersion forces and dipole-dipole in COS. Okay, and they love asking those questions. In this case, yeah, see, that's the thing, Haley, is they love asking these kind of problems where they'll give you some sort of data that contradicts just memorizing hydrogen bonds are stronger than dipole-dipole, which is stronger than dispersion. And so you have to be able to explain how mass comes into play and how mass has a factor. And in this case, it turns out that mass is a bigger factor than polarity. Now, there's other cases where polarity is more important than mass, and there's all these other things that happen. So that's why you have to be able to use the data they give you and explain it from the data rather than just memorizing trends and properties. So, yeah, this is a great problem. I'm glad we went over this one. I guarantee there will be something like this on this year's test. 100%. Okay, 95%. I can't say 100%, but like I'm 90 something percent confident. So if it was CCLS, yeah, or if it was like, let me think of a periodic table. Yeah, or if it had like selenium on there, maybe it would be stronger, or something. But yeah, chlorine would probably be stronger. Yeah. But chlorine would only form one bond, and so saying chlorine's a little tricky. So the thing is, though, you would just have to look at the data they give you, right? you know that higher boiling point must means it has stronger forces. Shoot, I'm out of time. This is just a P equals nRT problem. You guys should be able to do P equals nRT, no problem. Let's see. Percent ionization of a weak acid. They're probably not going to ask something about this, so I'm going to skip this. This is electrochem, so we can skip that. Did you guys get number 7? Number 7 should have been easy. So this is a PES, right? Photoelectron spectrum. I'll spend the last couple minutes going over this one. So a reminder, photoelectron spectrums, right? The y-axis is traditionally backwards. You'll notice 45, 40, 35, it's going down, right? And that's an attempt to show core electrons versus valence electrons. And remember, the height of the peak tells you how many electrons there are. And so this is an S, so this is 1s2, 2s2, 2p3. So 1s2, 2s2, 2p3. That would be element nitrogen, right? Because we have a total of 1, 2, 3, 4, 5, 6, 7 electrons. And so they're trying to show 1s, 2s, and 2p. So our element here is nitrogen. And then they give us, and then they throw a rate law in here. Cool. Calculate the value of the rate constant K for the radioactive decay. Identify the units with your answer. So they give you a half-life. So on the formula sheet, you have the half-life equation. So our half-life equation, if you remember, is that the half-life is equal to the natural log of 2 over K. And so if that means if it's 10 minutes, that equals 0.693 over K. So K equals 0.0693 minutes to the negative 1, right? Multiply by K, divide by 10. So 0.0693, and then the units are important here, minutes to the negative 1. And then part C of this one, Part C of this one then asks, if 64 atoms of the radioactive isotope are originally sampled in the principle, what is the expected amount of time that will pass until only 1 atom remains? That's fun. Okay, so there's a couple ways to go about doing this. I think just using the integrated first order rate law works. So remember, the integrated first order is the natural log of A at time t equals negative kt plus the natural log of A initially. And if we subtract it, we get the natural log of AT over A naught equals negative KT. We should be able to solve for time, right? If we start out, if we want 1 over 64 equals negative 0.0693 times T, and that's minutes. We should just be able to plug that in. With half-life, yeah, because first order is always time to the negative first, because a first order half-life, or a first order K is always just time to the negative 1 power, per minutes, per seconds, per hours, whatever. So 1 over 64 natural log divided by 0.0693 negative, I get 60 minutes or 1 hour. That's kind of cool. Is that what they say? Oh, cool. Yep, that is what they say. So they say the element is nitrogen, right? 0.069 per minutes. They gave you points for the units on this one. Right? So if they ask a question about K and ask you to solve for K, there will almost always be a point associated with units. So remember, first order is always just going to be time to the negative 1 power. You could figure that as well, because this natural log of 2. These are from the equation sheet, Naya. So here, look, let me show you. Whoop. So here's our kinetics, right? So we have, here's the half-life equation. Right? T1 half 0.693 over K. And then here's our first order rate law. Natural log of the concentration of A, natural log of the concentration initially equals negative KT. And properties of logs, you can just combine those together. right? And when you subtract logs, it's the same as dividing what's on the inside. So yeah, this is on the equation sheet. So yeah, so 0.069, and then you could just, so you could have done like counting. You should say, oh, 64, 32, 8, 4, 2, 1, that's 6 half-lives, 60 minutes. Or you could have used the equation. This first method might have been easier, but this one works too. So, but you have to show your work in either case, and you get an easy point. In my opinion, this problem's a really easy 4 points. So hopefully you guys felt the same. It's 11 o'clock. I don't want to hold you guys any longer. I will go ahead and upload this stream. I'm going to publish the 2019 exam. That's my last free response full exam I have to give. And next week we're going to be going over just some more. I have some other free response questions that we'll pull. Maybe I'll put out a survey to see like what topics you guys want to see more questions on. That way I could maybe like on Monday we could do a whole bunch of questions on rates, or we could do a whole bunch of questions on intermolecular forces, or I could go through and try to find a bunch of questions on a specific topic. I think I'll do that. I think I'll try to find questions on each topic that we've been talking about. I'll go through and pull some stuff. So that's what we'll do next week. I'll walk you guys through some problems. And then, yeah, for sure, Naya, we'll develop kind of a cheat sheet to reference. We'll do that. I don't know if I want to do that next week. We might do that the following week, like the week of the AP exam. Maybe that Monday or Wednesday. That's kind of some final preparation material. Maybe we'll do it next week. I'll figure something out. We'll do something. We'll do some sort of a Gillespie reference sheet that we'll compile together. Anyways, have a good weekend, guys. Take a break. It's going to be a little rainy today, but find some time to get outside. We're relaxing social distancing in the case of Utah, so you can start to like go to hair salons and dental offices and places like that starting today. So that's something that keep in mind. Some restaurants are opening with like more spread out seating. So yeah, do something. Get out, do something. So, oh, hi Claire. You want to come say hi? Come here. Can you say hi? What are you eating? You're eating goldfish. Can you say hi? Say hi. Can you show everyone what's in your cup? Your little tea set? Put it on there. Good job. You're cute. Say bye. Can you say bye-bye?
Bye.
Bye.